In the previous lecture, we covered rotor torque at standstill. In today's lecture, we will start our discussion on rotor torque of an induction motor under running condition. From our previous lecture, we know torque is proportional to phi rotor current. As we are considering under running condition, that's why I am not putting I2 prime. 2 means the current at the rotor side and prime means the value at standstill. So here we are considering the current at the rotor side under running condition and cos theta 2. That is also the power factor under running condition. Now if we recall the rotor equivalent circuit, we know the current through this rotor phase depends on this induced EMF in the rotor side. So this current per phase can be written as I2 equal to E2 over Z2, where Z2 is the impedance here, which can be written as S into E2 prime, where S is the slip. We know induced EMF in the rotor side under running condition is equal to induced EMF in the rotor side at standstill multiplied with the slip. And Z2 can be written as R2 square plus X2 square. And from our previous lecture, we know this x2 can be written as S into x2 prime, where x2 prime is the per phase reactance at the rotor side at standstill condition. So this equation can be written as S into E2 prime divided by root over R2 square plus S into x2 prime whole square. Similarly, cos theta 2 can be written as R2 divided by root over R2 square plus S into x2 prime whole square, as we are considering the running condition. Hence, the torque under running condition tau r is better under running condition if we denote it by r. So we can write r here is proportional to pi magnetic field into, instead of I2 we'll write this S into E2 prime divided by root over R2 square plus S x2 prime whole square into R2 divided by root over R2 square plus S into x2 prime whole square. As we know, phi is directly proportional to E2 prime, which was described in the previous lecture. So we can write from here phi is proportional to E2 prime. So tau r is proportional to E2 prime into S into E2 prime divided by root over R2 square plus S x2 prime whole square into R2 divided by root over R2 square plus S into x2 prime whole square, and we can write tau r is proportional to S into E2 prime square into R2 divided by R2 square plus S x2 prime whole square. If we equate them by putting a constant here, so our tau or torque under running condition is equal to K into S into E2 prime square into R2 divided by R2 square plus S x2 prime whole square. So this is the torque equation under running condition. Here k is constant. The value of k can be proved to be equal to 3 by twice pi ns, which will be shown later. We know at standstill the value of slip will be equal to 1. So if we put value of slip equal to 1, we'll get the torque at standstill. That means starting torque. So at standstill, the value of slip will be equal to 1. From here we can get the tau. At standstill we can name it tau is equal to k into, as is equal to 1, we are writing only e2 prime square r2 divided by r2 square plus x2 prime square. And this is the torque equation that we got in our previous lecture as a starting torque, which is also obtainable from the torque equation under running condition by putting s equal to 1. So this is the torque equation at standstill condition. And this k is constant value. The value of k can be found out as k equal to 3 over twice pi ns, where ns is the synchronous speed in rps, rotation per second. I'll show you the proof later, time permits. For the time being, we'll assume that k equal to 3 by twice pi ns. If you remember the torque equation under running condition, then from here you can figure out the torque condition at standstill condition. If you put s equal to 1, you'll get this equation. And when we'll get s equal to 1? At standstill condition. At standstill condition, we know slip value equal to 1. If we put slip value equal to 1 at the running torque equation, then we'll get the torque equation for starting condition, because when the motor starts, the rotor is at standstill. At that moment, the torque that is produced is called starting torque. Now let us analyze the rotor torque at two different conditions. Rotor torque at standstill. So at standstill, means slip equal to 1. We have got our equation tau is equal to k constant. We know k equal to 3 by twice pi ns, where n is in rps, into 2 prime square. That means induced EMF in the rotor side at standstill condition multiplied with R2, rotor resistance. R2 is the rotor resistance, divided by R2 square plus x2 prime square. Now what will happen if we change the rotor resistance? We know that this rotor resistance cannot be changed in squirrel cage rotor condition. However, from our previous discussions, we know that we can change the rotor resistance. That means we can add some rotor resistance for own rotor case. Now, before we add rotor resistance at the own rotor side, we need to know what will be the case if we change the rotor resistance. So if we change the rotor resistance, what happens to the starting torque? We'll check it out. This equation is second order equation for rotor resistance variable, and it will be nonlinear. Let's see, if we keep all other parameters constant and if we change the rotor resistance, how the starting torque behaves. Now if we plot R2 versus tau s, the plotting will look like this. At x direction we can take R2, that means rotor resistance, and we'll have increment in this direction. And in y direction we can take starting torque tau s. Hence the curve will look like this. Now when R2 is equal to 0, the starting torque will also be 0. But in practice it is impossible to get R2, that means rotor resistance, equal to 0, because whatever material we use, there must be an internal resistance, though it is very low, but there must be an internal resistance and practically R2 cannot have zero value. From here we can see for certain R2 value, we can get the maximum starting torque. This is maximum starting torque. So this is tau s max. Now in which condition we can get this maximum point? In order to get that, if we take the differentiation of tau s with respect to R2 and consider the value equal to 0, then we'll get this peak. Now let us find out the condition for maximum starting torque. As I told you earlier, in order to get this maximum point, we need to take the differentiation of d tau s with respect to R2 and equate it to the value of 0, because at maximum point, peak point, the differentiation value of this curve will be 0. So if we write it, tau s equal to 3 over twice pi ns into E2 prime square into R2 divided by R2 square plus X2 prime square is the whole differentiation equal to 0. Now if you solve it, you'll get R2 equal to X2 prime. I want all of you to solve from here to here using your basic knowledge on solving differential equation. So the condition for maximum starting torque should be R2 equal to X2 prime. That means the rotor resistance should be equal to the reactance of the rotor side at standstill. So whenever we'll get the maximum point, this R2 value should be equal to X2 prime value. Now try to understand one thing. If you keep increasing the rotor resistance, the starting torque will be increased. Now if you need a higher starting torque for a particular induction motor, what you need to do, you need to increase the rotor resistance. Now increasing rotor resistance is not possible for squirrel cage condition. It is only possible for on rotor case. Externally we can add resistance with the rotor side. So if we keep increasing the rotor resistance, the starting torque will be increased. Now remember, after a certain value, what is that certain value? When R2 reaches to the value of X2 prime, that is the reactance in the rotor side, then even though you keep increasing the rotor resistance, the starting torque will start decreasing. So you cannot increase the rotor resistance indefinitely for higher starting torque. Keep it in your mind. Suppose for a particular motor, you want to start the motor with higher amount of load. What you need to do, you need to increase the rotor resistance, and later on you may decrease the rotor resistance. I'll show you in detail what is the benefit of decrement the rotor resistance under running condition. But for starting condition, by increasing the rotor resistance, we can increase the starting torque. Now let us see the torque speed characteristics under running condition. So the next topic is torque speed characteristics under running condition. Definitely it will be under running condition because we are considering torque speed. When speed is involved, that means the motor is under running condition. So let's see how the characteristics look like. This is the torque equation at a standstill condition. That means the motor is at a standstill, the rotor is not rotating. Now under running condition, under running condition, the torque equation tau r, we got it 3 over twice pi ns into, the equation is similar to this one, but instead of writing it e2 prime square, we need to multiply that value with a slip. The slip value varies with the speed. So e2 prime square into r2 divided by r2 square plus s into x2 prime square, as we saw it in the previous page. Now for a particular rotor resistance and keeping other parameters constant, if the speed of the rotor is changed, that means this S value will also be changed. When the speed is higher, the S will go near to the 0 value. When the speed is lower, then S will go near to the 1 value. And when it is stopped, S has the value of 1. I hope all of you remember this equation. S equal to Ns minus Nr over Ns. When Nr equal to 0, then S becomes 1. As Nr increases, S goes near to the value of 0. Under the motoring operation, the S value ranges from 1 to 0, depending on the rotor speed value. Now, if we plot this rotor torque under running condition with respect to rotor speed, so in y-axis we'll take rotor torque, and in x-axis we'll take the rotor speed. Rotor speed, that is denoted by Nr. Here we'll change only the rotor speed, keeping other values constant. You can plot it using MATLAB or Octave software for this case and for this case as well. And for running torque, you'll get a curve which will look like this. This is the position where the Nr value will be equal to Ns. So here the value of Nr is equal to Ns. This is the maximum running torque position. We'll figure out the condition for maximum running torque, and from here to here, if we take this point, this is the tau r maximum running torque. This is the starting torque position, tau s, as Nr is 0 here. So if we consider rotor speed, then rotor speed will be 0 here. At 0 speed means slip equal to 1. At slip equal to 1, whatever the value of tau will get, that is the starting torque. So this is the starting torque position. Remember, this starting torque position can be increased or decreased by changing the rotor resistance, as we saw from here. So this value can be increased or decreased. We'll see the characteristics on changing rotor resistance for different cases. If we consider the same for slip, here when Nr equal to 0, the slip will be equal to 1, and when Nr equal to Ns, the slip will be equal to 0. So slip will be 1 here, slip will be 0 here. So if we take another axis, this is another axis, this is for slip case, then slip will be 1 here and it will have decrement in nature. Now we have two regions. One is before the maximum torque point and another one is after the maximum torque point. Before the maximum torque point, this region is called unstable region. Unstable region. And this region is called stable region. Why is this called unstable region? Because motor cannot have a fixed operating point in this region, but here it is possible. How? I'm going to describe it. But before that, I want all of you to know that this characteristics curve is the rotor's produced torque curve. Now the operating point will be exactly at the same point on the load torque. Motor must produce an amount of torque that is exactly same as the load torque. Then in that condition, motor will run stably with a fixed speed. So if we have the load torque tau L, so in order to run the motor in stable condition, the motor must produce exactly same amount of torque. So if we say that motor's produced torque is tau P, So tau p produced torque should be equal to the load torque. Then motor will run with a fixed speed. If the produced torque is higher than the load torque, then what will happen? That increased amount of torque will increase the rotor speed, and motor will gain the exactly same operating point as load torque. For example, suppose we have a load torque at this point. Okay, so this is the load torque tau L that is connected with the motor shaft. So when you switch on the motor will start from this zero speed, and the speed will keep increasing, and it will follow this line, and it will come here, and the operating point will be like this. That means here this line is the motor's produced torque, and this line is the load torque that is exerted on the motor, and they must be same. So in this point they are equal. The produced torque is equal to the load torque. So this will be the operating point. At this operating point the rotor speed will be this value. Now if we increase the load torque, what will happen? Suppose we have increased the load torque, and this is the new load line. Then what's happening? The operating point will shift from here to here. So motor will start producing more torque in order to face that new torque. And as motor is producing more torque in order to meet the requirement of load torque, so the speed will be decreased. New speed will be here. So speed is decreased. Previously rotor speed was this. Now after exerting the new load, then the speed will be decreased and motor is producing more torque. So as we keep increasing the load, the speed will be decreased, and this is normal phenomenon. That means whenever we'll increase load, the motor will start producing more torque and the speed will be decreased. If we decrease load, the motor will start producing less amount of torque and the speed will be increased. Now when the motor starts at zero speed, suppose this was our initial load connected, we consider this load line. At that moment the starting torque is higher than the load torque, so motor will start. When motor starts, the torque gives a force to the rotor, so the rotor gets some speed. When rotor gets some speed, at this point due to that speed, again the rotor finds that torque is already increased here, produced torque. So rotor again gets another thrust. So rotor speed keeps increasing. So when it comes here to this speed, again rotor produced torque is also increased. So as rotor's produced torque is increased, that means rotor keep getting the thrust. So rotor cannot be stable in any point, rather it keeps going in this way, keeps going. Now after sometimes it crosses the maximum point, then it finds that, well, my load is this amount, so it starts reducing the produced torque because load torque is lower than this amount of torque, so it starts reducing the produced torque. When it starts reducing the produced torque, at that cost the speed is getting increased. If we move in this direction, the speed is increased. So from here it's coming here. Now it's not the load torque. Again it comes here, it's not the load torque because load torque is here, so it keeps increasing the speed. When it comes here, it finds that the produced torque is exactly same as the load torque, so motor starts running stably in this position. If we look into our normal fan, when we switch on our fan, what happens? At the very beginning the rotor starts increasing the speed, and it keeps increasing. After sometimes rotor starts running with a stable speed, and that is the stable point which is denoted here. Suppose for fan the three blades are the loads, so it starts producing exactly same amount of load, and for that amount of load it has a stable point, and with that stable point it starts, or it keeps running stably with a fixed speed. So we have understood that motor can run stably in this region, but motor cannot run stably in this region. Rather, for switching on, the motor will follow this path, and when we switch off the motor, it will keep decreasing the speed. In this way, following this path, it will come to this standstill condition. I hope this is clear to all of you. We'll continue from here in the next class. Thank you.